So this is a video of Chapter 8, which is called Bonding General Concepts. Our outline is types of bonds, electronegativity, bond polarity, ionic compounds and energy effects, covalent compounds, Lewis structures, formal charge that we actually will talk about in not these lecture notes, but in an activity, shapes, polarity, and bond energies. Types of bonds. A chemical bond is a force that holds atoms or ions near one another. Bond energy is the energy required to break the bond. From a simplistic point of view, bonds form when separate atoms are higher in energy, like carbon plus 4 hydrogens as separate atoms, than collections of atoms, that is, the compound formed from them. So the C plus H4 is at a higher enthalpy position, higher energy, we could say, than is the compound that forms from them, CH4. That's lower energy, more stable. It's lower in energy by this 1652 kilojoules per mole. And that is basically the reason that CH4 would form from the atoms, carbon and hydrogens. The two common bond types, and we'll see there are more, but two very common ones are the ionic bond and the covalent bond. The ionic bond is the bond that forms between cations, which are positive ions, and anions, which are negative ions, due to the opposite charges of these ions. So it's just that electrostatic attraction between plus and minus. The covalent bond is a bond between atoms due to sharing of electrons. So the atoms are actually by each other, and electrons are between them, between the two nuclei, where these electrons are simultaneously attracted to both nuclei. Of course, you know electrons have a negative charge. Nuclei with the protons have a positive charge. So plus minus attracted to each other. So the electrons between the two nuclei are attracted to both nuclei. We call that type of a bond where there are electrons between the nuclei, we call that a covalent bond. So going back to the left side of that table, the ionic bond, when sodium is the atom, it has the electron configuration Ne3s1. By the way, get a periodic table. Maybe stop the video and get a periodic table to have that beside you if you don't already have it available. So sodium, neon, 3s1. Chlorine, neon, 3s2, 3p5. So it turns out that when those two atoms come together, chlorine so much wants an electron, and sodium doesn't much mind losing an electron, that the electron goes from the sodium, that valence electron, that 3s1 electron, goes from the sodium atom to the chlorine atom, making Cl minus. Now, the sodium has the electron configuration of neon, and the chlorine, the Cl minus, has the electron configuration of argon. As we will see as we go on in this chapter, having an electron configuration of a noble gas is particularly low energy, stable, and is often we can often use that as the reason that certain kinds of compounds form, both the ionic type and covalent type. Okay, so going to the right half of the table, the covalent bond, when we have two chlorine atoms, they can come together to form Cl2, the molecule, where between those two chlorine nuclei are two electrons that are those covalent electrons that are the covalent bond. Each chlorine atom has the electron configuration as we talked about before, neon 3s2 3p5. And so we see what that would look like. Now, if the chlorine electron on the left and the chlorine electron on the right can get a little bit closer such that they each have access to those two lone electrons from the chlorine atoms, they can form a chlorine molecule. They can form a covalent bond. So what we see is the diagram of the valence electrons shown around the two chlorine nuclei with their core electrons, showing that each chlorine atom now has access to 8 electrons. So the one on the left, the 2 electrons above, the 2 to the left, the 2 below, the 2 in between the two nuclei. So that makes 2, 4, 6, 8 for the chlorine on the left. Same deal for the chlorine on the right. It has access to 8 electrons. Its original 6 plus the 2 shared ones. And each has 8 electrons, and that is a kind of magic number that we will see again. That has to do with the octet rule. Okay, our next topic is electronegativity. We talked about that in chapter 7. Remember that we had the definition, it's the ability of the atom to attract shared electrons to itself, and the trend is to increase going from left to right and to increase going from bottom to top on the periodic table. That means fluorine has the highest electronegativity. The most of all the elements, minus the noble gases, wants to attract electrons to itself. Our next topic is bond polarity. So consider the bond between an atom A and an atom B. If we know the electronegativity values of each of those atoms, then we can use that information to determine which type of a bond will form between those two atoms. So we calculate the change in electronegativity between the two. We take the larger electronegativity value and subtract the smaller one from that. So delta En is what we're after. In our case here, let's say that A has a larger electronegativity. We would calculate delta En to be En A minus EnB. If that number is large and our cutoff point is 1.9, if it is greater than 1.9, then we would say that one atom has such a much greater desire to pull electrons to itself that it actually will pull an electron from the other atom to it. And we will end up with an anion and then a cation, and the compound would be an ionic compound, and the attraction would be the ionic bond. So as delta En increases, the percent ionic character increases. Looking at table 8.1, we see that in comparing atoms, if the difference between the two, the electronegativity difference, the delta En is 0, then we have a covalent bond. In fact, we have a pure covalent bond, all covalent character. If the electronegativity is large, greater than 1.9, then we call that an ionic bond, so we have high ionic character. If it lies somewhere between the two, so it's not 0, but it's not greater than 1.9, then we would call that a covalent bond, but it definitely is a polar covalent bond. That means the electrons spend more time on one atom, the more electronegative atom, than the other. So some examples of this, we'll look at the molecules H2, HCl, and then the ionic compound NaCl. In H2, we have, of course, two hydrogen atoms bonded together. Their electronegativity difference is 2. They make for a covalent compound. A covalent bond is between the two nuclei. They have equal sharing of electrons, just a straight covalent bond. In HCl, if we look up the electronegativity values, they're in the chapter 7 handout notes. They're also in your textbook. We would find the value for chlorine is 3.0. The value for hydrogen is 2.1. So we do 3.0 minus 2.1. We get delta En to be 0.9. That is less than 1.9, but is not 0. So being less than 1.9, it's a covalent compound that forms. Being greater than 0, it would be a polar covalent type bond that forms. Now, what that translates to for us is the electrons between the H and the Cl, and there are 2 of them, those spend more of their time closer to the chlorine than the hydrogen, or just evenly between the 2. We would say that the chlorine end has a slight, or we would say partial, negative charge, leaving the hydrogen end having a partial positive charge. And partial is often expressed, at least in this context, using the Greek symbol delta. And that's that delta plus by hydrogen and then delta minus by chlorine. So this molecule has a covalent bond, but electrons are not shared equally, so the bond is a polar covalent bond. The molecule HCl contains a dipole moment. We'll see that term come up again in this chapter, where a dipole moment is a separation of charge, a separation of charge, like a partial plus end and a partial minus end. If we look at NaCl, look up their values, we have chlorine from above, 3.0, Na 0.9, so we do 3.0 minus 0.9, we get delta En to be 2.1. It's greater than 1.9, so we would say that bond is an ionic bond, the compound is an ionic compound. Looking at the diagram on the bottom left, we have the molecule HF, which is very much like HCl in being a polar molecule. The fluorine has the partial minus charge, the hydrogen the partial plus charge. Now, if we have in our diagram the hydrogen represented by blue, the fluorine by green, if we have no electric field there, then the molecules are just randomly oriented. Sometimes hydrogen up, sometimes down, sometimes left, sometimes right. But if we apply an electric field, so we have a minus end on, let's say, the left side and plus end on the minus side, then we find that in all those molecules, the H would be closest to the minus side and the fluorine closest to the plus side. The table or the graph there, percent ionic character versus electronegativity, what it is showing us is as electronegativity difference increases, as we move to the right on the x-axis, we get greater ionic character. We have a bigger delta En, because that's what energy electronegativity difference is. It's delta En. So greater delta En, greater ionic character. And what's shown in red are the ionic compounds, and they have a big electronegativity difference. They have great ionic character. The hydrogen compounds that are shown in blue and the other ones shown there in blue, those have small electronegativity difference and they have small ionic character. What to notice is that it's not that we have just covalent or we have just ionic. We actually have like a spectrum between. Some ionic compounds have more ionic character than others. They have, If they have more ionic character, they have a greater total losing of electrons from the 1 to the higher electronegativity 1. Okay, our next topic is ionic compounds and energy effects. So we're going to talk now about ionic compounds, and we'll make some energy calculations. And then we will talk about covalent compounds. So ionic compounds. Looking at LiF, lithium fluoride, the lithium as an atom has the electron configuration helium 2s1. The fluorine as an atom has helium 2s2, 2p5. Li plus is what forms, and what happens is that 2s electron is transferred to the fluorine. So Li plus has the electron configuration helium. That makes it stable. The fluorine minus has the electron configuration of neon. Again, that makes it stable. So energy effects explain why ionic compounds form, and that's what we'll look at next. Losing electrons takes energy, and gaining electrons sometimes also takes energy, sometimes gives off energy, but losing electrons always takes energy. Since large amounts of energy are given off when cations and anions come together due to their opposite charges and the great attraction between opposite charges, the overall ionization process is usually exothermic. So let's see that stepwise. The large amount of energy given off when a cation and an anion come together is called the lattice energy, abbreviated LE. So lattice energy, LE, is the change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. So it's the energy given off when minus and plus in the gas phase come together. And it's shown by the reaction M plus, some kind of metal with a plus charge as a gas, plus X minus, a nonmetal with a minus charge as a gas, come together to form MX, the solid ionic compound. Okay, we will look at the formation of LiF from its elements. So we have lots of steps. In fact, we have 5 steps we'll look at. Ultimately, we will calculate the energy that either it takes or is given off, in this case is given off, is exothermic, when Li solid plus 1/2 F2 gas form LiF solid. Li solid, that's how lithium as a metal exists at room temperature. F2 gas is how F2 exists at room temperature. And then LiF is the solid that forms when they come together. Okay, so what's delta H? So the first process is we have to sublime the lithium solid. So that takes energy. It always takes energy to go from solid to liquid to gas. In this case, we're going directly from solid to gas. That takes energy. In the case of this lithium, it takes 161 kilojoules per mole. That would be delta H for that step 1. Then we'll look at ionizing it. That also takes energy. So we're going from Li gas to Li plus gas plus an electron. We've pulled away the electron. That takes 520 kilojoules per mole of energy. Okay, so for the moment we're done with lithium. Now looking at the fluorine. So 1/2 F2 gas to F gas. So what we're doing is we're breaking the F2 bond. That takes energy. It always takes energy to break bonds. So that takes 77 kilojoules per mole of F atoms formed. Now we'll look at forming the ion. So F gas, F the atom gas plus an electron, forming F minus the gas. That actually gives off energy, and the amount is 328 kilojoules per mole. Now we've got Li plus gas, we've got F minus gas. It has taken energy somewhat to get to that point, but forming F minus gave off a little bit of energy, but when Li plus and F minus come together to form the ionic compound, a tremendous amount of energy is given off. That is the lattice energy, Le. So we have Li plus gas plus F minus gas forming LiF solid. We see that 1,047 kilojoules per mole of energy are given off, so negative, exothermic. Now, kind of like we did in the last chapter using Hess's law, if we add those 5 reactions together, getting rid of what appears on both sides, we have the overall reaction Li solid plus 1/2 F2 gas yields LiF solid, and if we add up all the energy change values, we get that to be negative 617. So we have determined what delta H is for that reaction, and we see that there. So it's exothermic. This energy diagram shown at the bottom of the page is a visual way to see all the steps and whether they take energy that is climb upwards or give off energy that is go downwards. So we have the lithium solid and the fluorine gas, 1/2 F2. There, we begin there, we add 161 kilojoules, we get Li, the gas, to form. The fluorine not affected yet. Then we add 520 kilojoules, that's step 2, and now we get fluorine still the same, but we have Li plus, so we've ionized it. And then we add a little more energy, 77 kilojoules, that's step 3. Now we go from fluorine F2 the molecule to F the atom. We have not changed lithium in this step. Now step 4, notice the arrow goes down because energy is now starting to be given off as we go from fluorine the gas to F minus the gaseous ion. And then we have what the cation and anion can come together to give us the lithium fluoride ionic compound, and we get a huge amount of energy given off. That's step 5. Once again, that's the lattice energy step. The structure of LiF, shown on the right in that table, that is showing the fluorine as the green ball, the lithium as the purple ball. It's shown in 2 different ways. Look at the bottom, look at B. That one is more realistic of what the real ionic compound looks like. Note that although we write LiF, we don't write Li many, F many. That's because in the ionic compound chemical formula, we are just simply writing the simplest ratio. For every 1 Li plus, there's 1 F minus, even though a crystal of lithium fluoride, which would look a lot like a crystal of sodium chloride, would have many lithium ions, many fluoride ions. In our diagram, it might look like the fluorine touch each other, but of course F minus repels F minus, so the F minus and F minus do not touch each other. They're touching the Li plus. So the structure is such that it maximizes the cation-anion attractions and minimizes any cation-cation or anion-anion repulsions. Okay, here's an example to work on your own, so make note to do that. You're given the processes for forming calcium chloride from its elements. You're after calculating delta H, so run through that one on your own. This next problem is having you write the lattice energy equation for the formation of MgO. So you'll have to look back above to see what is lattice energy, which step is that, and what it would be for that particular compound. And then take a look at the diagram for it, which is the one on the left. And you can, in there, determine what that energy value is. So the lattice energy, Le, that's the one that has cation and anion coming together. That is proportional to Q1 times Q2 divided by R. The Q are the charges of the cation and the anion, like +1, -1, and the R is the distance the ions are apart. Notice that the Q's are up in the numerator, so the bigger the charges, the greater the lattice energy, the greater the amount of energy given off when the cation and the anion come together. R, that is in the denominator, so the smaller it is, the bigger the lattice energy. The smaller it is, that means the closer the ions are to each other. So those are two factors, charge factor and size factor, that are going to figure into the attraction. So in this table on the left, we're comparing sodium fluoride and sodium chloride and so forth, all the way down to sodium iodide. Looking at the periodic table, we see, of course, sodium is the same for all of them. What changes is the halogen. Fluorine is smaller than iodine. So the charges of the Na+, the X minus, the halide ion, those are the same for all four of those examples. It's +1, -1. So that would be the same. But the R is very different between them. We have NaF having the closest, the smallest R value. The ions are closest together. In NaF, they are the farthest apart, so we have the longest radius, or the greatest separation. And that's reflected in the values of the LE, of the lattice energy in kilojoules per mole. For NaF, we see the amount given off is 923, whereas in NaI it is less, it is 704. So as R increases, the lattice energy decreases, or we could say as R decreases, the lattice energy increases. The second table is comparing R's, but mainly Q values. So in NaCl, we have +1, -1. In MgS, we have +2, -2. It turns out that the radii, the separation of the ions for those two different compounds, is pretty close. So we'll say those values are about the same. R is about the same. So we're just looking at the charges. And if we have +1, -1, we don't have as big a lattice energy value, because there is less attraction between plus and minus than there is between +2 and -2. So we see a huge difference in the lattice energy between the MgS compound and the NaCl compound. So here's another example for you to work at in each pair, which has the larger lattice energy, just based on what you can determine about the relative sizes and what you can know about the charges based on their structure. Okay, so that's ionic compounds and those energy effects. Now we will talk about covalent compounds, and there's actually a lot to talk about with those. So in general, a chemical bond is a force that holds atoms or ions near one another. Atoms in covalent compounds, ions in ionic compounds. Bond energy is the energy required to break the bond, to break whatever that type of bond is, ionic, covalent. Okay, as we talked about earlier, from a simplistic point of view, bonds form when separate atoms are higher in energy than collections of atoms. Okay, and we have that diagram, that energy level diagram, enthalpy versus time for the formation of CH4 from C and 4 H's. So we see the product at a lower energy, which would explain why that one would form. Atoms come together to form compounds because the compounds are at a lower energy. When non-metal atoms bond together, a covalent compound results. So now we're in just covalent compounds. The atoms are stabilized in the compound by sharing electrons. often achieving a noble gas electron configuration. So we alluded to that in our discussion in this chapter a bit already. Helium's noble gas, or helium's electron configuration is 1s2. It has 2 valence electrons. It has 2 electrons total. Neon, argon, we see the electron configuration of neon. Helium, 2s2, 2p6. It has 8 valence electrons. Argon, neon, 3s2, 3p6. It has 8 valence electrons. Okay, so those numbers, the 2, the 8, are kind of like magic numbers. So for row 1, having 2 electrons, having a duet helps with atom stability. Hydrogen follows the duet 2 rule, duet for 2. So the duet rule, it likes 2 electrons. It likes access to 2 electrons. It only has one H, the atom, and that explains why hydrogen bonds with lots of different atoms so that it can get access to a second electron. For row 2 and beyond, having 8 electrons, an octet, octet having to do with 8, helps with stability. These atoms often follow the octet rule. So they might not have 8 electrons just on their own, but they form bonds in such a way that they end up with access to 8 electrons. So we will go on now to talk about structures and shapes, and that is very useful for a chemist to know. Structures. CH4 is a structure. It tells us that one carbon has 4 hydrogens bonded to it. In NH3, we have 1 nitrogen with 3 hydrogens bonded to it. For a chemist, that would be very important to know if that chemist were interested in CH4, which is methane, or NH3, which is ammonia. Okay, shapes. Shapes are very important to us. We have talked about that water has a bent type shape, and we will definitely go into that more in this chapter. It turns out having that bent shape determines many properties of water that makes life as we know it the way it is, as opposed to being very different if, for example, water were linear instead of bent. Bond strengths, well, if we need to break bonds for some reason, then we like to have a sense of bond strengths. When we have a double bond, as we do in oxygen, the atom, it's a stronger bond than a single bond, which is, for example, present in F2, the molecule. So O2 has a double bond. It's harder to break that bond than the bond in F2, which is a single bond. A double bond has 4 covalent electrons there bonding those atoms, those nuclei and core electrons together. A single bond is composed of only 2 electrons. Okay, so now we will get into how to draw structures, which we call Lewis structures. And we'll get into the rules for drawing them. You probably had exposure to this in a previous chemistry class. In fact, it's assumed that you have. And you learned how to draw Lewis structures. If you like the way you were taught that and it works well for you and it works well for the molecules we'll deal with, go ahead and do it that way. If you want to try a new way, or maybe this way I'm going to show you is the way you learned before, super. Whatever way you use is fine with me, provided basically that it works. Okay, so my set of rules are: 1, determine which atom is the central atom. The central atom is usually the atom with the lowest electronegativity value, is often written first in the chemical formula, and often only contains one of these atoms in the chemical formula. So, for example, CH4, the C is written first. We could assume it goes in the center. There's only 1 carbon as opposed to 4 hydrogens. Another reason it probably goes in the center. it turns out that hydrogen always goes on the outside because, or at least for our class, always goes on the outside according to the duet rule. It doesn't want access to any more than 2 electrons. If we try to put it in the middle, it would end up with access to more electrons, which it does not like. Okay, so these rules, this central atom, guessing what is a central atom, these are guidelines. There's exceptions. Okay, next we draw the skeletal structure by surrounding the central atom with the other atoms. So we've decided what goes in the center, we put it in the center, and then we draw the other atoms around that. Number 3, determine the total number of electrons in the structure by, not the total number, I would say determine the total number of valence electrons in the structure by summing the valence electrons of all of the atoms in the molecule or ion. Now, if it's an ion, something like NH4+, so an ion, a polyatomic ion, add 1 for each negative charge because it's got an extra electron, and subtract 1 for each positive charge because it's deficit an electron. Okay, so we determine the number of valence electrons each atom has, and we add all those together. And then we take care of any kind of a charge. Number 4, distribute the electrons among the atoms, giving octets or duets for hydrogen to as many atoms as possible. Begin by placing 2 electrons between each pair of atoms. That means a single bond. So you draw a dash for a single bond. Then distribute the remaining electrons. And that is to say, you're drawing lone pairs next. If any atom other than hydrogen or boron lack an octet, form double, which are 4 electrons, and it's drawn like that, looks kind of like an equal sign, or triple bonds, so that's composed of 6 electrons. These are called multiple bonds. Do this by moving lone pairs into bonding regions. Hydrogen forms a duet, and boron tends to form molecules with less than an octet. So those are the 2 main exceptions we will have to think about with respect to this octet rule. Okay, so what we have in Rule 5 is, if we can't give every atom its octet or hydrogen its duet, ignoring boron, then we start multiple bonds. Multiple bonds in general, are just giving atoms access to more electrons than they have on their own, because you're sharing electrons. So if it looks like in your single bond picture there aren't enough electrons for every atom to be happy, then start drawing in more bonds, draw in multiple bonds. Now, every time you draw in like an extra bond, a double bond, triple bond, what you have to do is realize those count from the total number of valence electrons. Okay, so that's if there aren't enough electrons, you do multiple bonds. 6, if there are too many electrons, and if the central atom is from row 3 or greater, row 3 or beyond, put the extra electrons on the central atom. This is called an expanded octet, so it has more than an octet. The formally empty 3d orbitals on the central atom can accommodate the extra electrons. So the big atoms, the ones that have access to 3d orbitals close enough in energy, they can put extra electrons in those orbitals. If the structure, Rule 7, if the structure is an ion, so like NH4+, once you're done with the Lewis structure, you would place square brackets around it and write the charge as a superscript on the upper right side. If there are multiple bonds, number 8, if there are multiple bonds in the structure, so if we didn't have enough electrons for a bunch of single bonds and lone pairs, so we had to draw multiple bonds. So if there are multiple bonds in the structure and they can be placed in different locations and still yield a valid Lewis structure, then the molecule has resonance. And you draw all resonant structures. Each structure has a multiple bond at a different location. Okay, so let's say that we drew a Lewis structure of SO3. So S is less electronegative than O, and there's only one of them, and it's written first. We would draw that in the middle. We would surround it by those 3 O's. We would determine how many valence electrons we're dealing with. So we have 6 for each sulfur, 6 for each oxygen. That gives us 24 electrons that we should see in our picture. First off, we would draw single bonds between the S and each of the O's. That would take care of 6 electrons. Then we would start drawing lone pairs around the O's and on the S. We would find that we don't have enough electrons to go around, giving everybody their octet, and so we would have to move some of those lone pairs. We would have to move 2 of them to between the S and one of the O's. Now everybody has an octet. Looking at that picture, as I wrote there, if this structure is correct, the 2 bond types would be different. We would have 2 singles and 1 double bond, and the double bond is stronger than the single bonds. Experiment shows that all 3 bonds are equal in strength, also equal in length. So the stronger the bond, the double bond, is shorter than the single bond. Okay, so that's what I mean by 2 bond types, different strength, different lengths. But experiment shows us that all 3 bonds are the same. So our picture is not quite right. That is to say, there is a multiple bond there, that double bond, and it could have been placed between the S and the O on the left. It could have been placed between the S and the O on the right. So we've got those 3 pictures down below, one with the double bond above, one with it on the right, one with it on the left. Those are the 3 resonant structures for SO3. And what they are trying to tell us is that SO3 is really a blend of all 3 structures. Resonance is invoked when more than one valid Lewis structure can be drawn. The real structure is like a blend or an average of all 3 structures. What those 3 resonance diagrams tell us is not that sometimes this double bond is up, sometimes left, sometimes right. Actually, it's telling us that that double bond is simultaneously up, left, and right, always. It's a blend of all 3, and that's how they're equivalent. Okay, now I give lots of examples for you to work with. So draw the Lewis structures for all of these molecules. And for SO2, there are resonant structures. Also for CO3 2-. Note that we also have a polyatomic anion, so you have to take that into account. CO2, CO, and then there's more NH4+, BF3. So remember boron, it does not mind an incomplete octet. It does not mind having less than 8 electrons around it. Also note that halogens typically make single bonds. So apply that to the next 4 examples. Formal charge we will cover in the activity on formal charge. Okay, so once we're able to draw the Lewis structure of a compound, from that we know what the central atom is, what kind of bonds there are to the attached atoms, whether double or single, etc. Once we have that, we can start looking at shapes. Like we know water is bent. We draw the Lewis structure of water, and then we apply what we're now going to talk about. So the shape comes about from a theory called the valence shell electron pair repulsion theory, VSEPR theory. Big name, but it mainly means that the shape, the structure, is determined principally by minimizing electron pair repulsions. So the bonding and non-bonding pairs of electrons around a given atom will be positioned as far apart from one another as possible. So for example, CO2 from above, you would have found that it looks like that. That's the Lewis structure. Carbon in the middle, double bond to O on the left, a double bond to O on the right. No lone pairs on the carbon, the oxygen, those each have 2 lone pairs. Now, those 4 electrons, those 4 bonded electrons on the left and those 4 bonded electrons on the right, they all have negative charges. They repel each other. The 4 electrons on the left are bound together. They're kind of locked together. The 4 electrons on the right are kind of locked together. But the 4 electrons on the left want to be as far away from the 4 electrons on the right as possible. And that's why they're completely opposite each other. So CO2 is a linear molecule, like that picture shows, looks like. It's not some kind of a bent molecule, because that would require that the 4 electrons on the left side are only 90 degrees as opposed to 180 degrees away from the other 4 electrons, the 4 bonded electrons. Notice that when we consider shape, we're looking at the central atom. How to get the electrons on that central atom as far away from one another as possible. Alrighty, so to use the table that we have below there, we have to know what is a group of electrons. So a group of electrons can be a lone pair. Some central atoms have a lone pair on them. It can be a single bond. That's one group. It can be a double bond. That's also one group. It can be a triple bond. That's also one group. Okay, so groups of electrons, lone pair, single bond, double bond, triple bond. Each one of those is a group, and every group wants to be as far away from any other group as possible, at least of the ones on the central atom. Alrighty, so in our table we have number of groups of electrons on the central atom, number of attached atoms, and then the shape following from that. So if we have a molecule that has 2 groups of electrons on the central atom, then we're in that first row. If it has also 2 groups of atoms, that means, or 2 attached atoms, that means you look at the central atom, how many atoms are attached to it. Okay, so if we have 2 there, then we have a linear molecule. That would be the case for CO2. So in our picture, we're not showing double bonds, single bonds, we're just showing a line representing whatever type of bond it is. So we would draw it that way. We would call it the shape linear if we were asked for the word name of the shape or the structure. We would say the bond angle is 180 degrees. So that takes care of all the possibilities where there are 2 groups of electrons on the central atom. If we have 3 groups of electrons on the central atom, then we have 2 possibilities. One is, to that central atom we have 3 attached atoms. If so, we have trigonal planar, and it looks like that picture. It's flat, it's a plane, it's a triangle, trigonal planar. The bond angles, all 3 of them, are 120 degrees. If, on the other hand, we have 3 groups of electrons, but only 2 attached atoms, Then we have the bent structure. That we would have if we have the central atom with 2 atoms attached and 1 lone pair. That gives rise to the bent structure, the bent shape. The bond angle is about 120. It turns out it's a little less than 120 because the lone pair of electrons has more space. It kind of moves around more than bonded electrons that are stuck more between the 2 nuclei. So it squeezes down the bond angle a little bit. Okay, so that takes care of 3 groups of electrons on the central atom. When we have 4 groups of electrons on the central atom and 4 attached atoms, we have the tetrahedral structure shown there. That looks like, well, it's a tetrahedron with the central atom in the middle of the tetrahedron. Imagine a pyramid with a base of 3 and an atom on the top of it. That would be the tetrahedral structure. Those bond angles are 109.5 degrees. And that's the shape that takes on when there are those 4 groups of electrons and they want to be as far away from one another as possible. Okay, so when there's only 3 attached atoms, we have trigonal pyramidal. So that's a pyramid with a base of 3 where we have a lone pair on the top. And that bond angle is a little less than 109.5 degrees, again for the same reason as in the bent structure from above. That lone pair moves around a little more than the bonded pair in the tetrahedral one, and so it squeezes those bond angles to be a little smaller than 109.5 degrees. The last one is what we have with water, and that is the one where we have 2 lone pairs on the central atom and 2 attached atoms. So again, we have 4 groups of electrons around the central atom, but only 2 attached atoms. So that would be water, and it's called bent. Bond angle, a little less than 109.5. In fact, in the case of water, it's 105 degrees. And that being, there's 2 lone pairs on the central atom roaming about, so squeezing that angle. Okay, so next we have 5 groups of electrons on the central atom. This, if you had Chem 110 here, you may not have been introduced to this structure, this shape, but definitely many compounds exist like this. So this is the expanded octet area. So if we have 5 groups of electrons on the central atom, and all of those groups are attached to atoms, then we have the shape that is trigonal pyramidal. So imagine we have an atom, and then in a plane, draw an atom to the left, draw an atom to the right, a little behind it, draw an atom to the right, a little in front. So that's a plane right there. It's a plane, it's a triangle with the central atom in the very middle of it. Now, put an atom above the central atom and an atom below the central atom. You have trigonal pyramidal. Bipyramidal. Trigonal bipyramidal. So it's like got that triangular base, but it's a pyramid above and a pyramid below. That's where the bi comes from. Those bond angles are 90 degrees as well as 120. Alrighty, so if we have 5 groups of electrons on the central atom, but only 4 attached atoms, we have what's called seesaw. If you tip that 90 degrees, you can picture a seesaw. Now the lone pair goes to the position on the left as shown in the diagram because lone pairs roam about more, and the closer they are to other groups of electrons on the central atom, the less stable. So the lone pair there, it is 90 degrees away from the upper one, the lower one. So 90 degrees away from two other groups of electrons. 120 degrees away from those other two, but that's a much bigger angle, so we ignore that. So it's 90 degrees away from 2. If we put that lone pair on the top instead of on the left, so let me go to our next page for a moment. So if we put that lone pair on the top, as that lower diagram shows, then what we have is that lone pair with its greater mobility than a bonded pair, it's 90 degrees away from 1, 2, 3 groups of electrons. That's not as stable than being 90 degrees away from only 2, like that upper diagram there shows. This page also shows the greater mobility of a lone pair. So here we have XH with the pink representing kind of like how the bonded electrons move about. They are fluid, they move. If we have just X with a lone pair, no other attached atom, then we have much greater movability of the electrons. Okay, and then just going on with the 5 groups of electrons on the central atom. Now there are 3 attached atoms, so we get what's called T-shaped. Again, tip that 90 degrees, and you would see that bond angle there. All 2 of those would be 90 degrees. Oh, in the seesaw shape, those bond angles are 90 degrees, as well as about 120, a little less than 120 because of the lone pair squeezing that bond a little bit, less than 120. If we have only 2 groups of electrons on the central atom, we end up with linear, 180 degree bond angle. Our last expanded octet situation is where we have 6 groups of electrons on the central atom, and we have 3 possible structures. We can have all 6 of those 2 attached atoms. Then we have an octahedron, the octahedral structure. So that is, imagine you have the central atom and you have 4 atoms in a plane around it with 90 degree angles. Then draw an atom above and an atom below, and you have octahedral. All bond angles are 90 degrees. If we have only 5 attached atoms, we take away one of those attached atoms, replace it with a lone pair. We have what's called square pyramidal. So it's a pyramid with a base of a square. If we have 4 attached atoms, we take yet one more away. Notice we take it opposite, 180 degrees apart. We take that one away, and that again has to do with lone pairs having more movability. They cover a greater space, and so they want to be as far away from one another as possible. And we have a plane with a base of a square. We call that square planar. Bond angles 90 degrees. Okay, so use that table in answering questions regarding shape, but you have to have already drawn the Lewis structure, so make sure you get that down. Read over this page. We went over most of it. Read over it on your own. Okay, our next topic is polarity. Polar molecules contain a permanent separation of charge, a permanent dipole moment. A dipole moment is, as we talked about before, just a separation of charge. Water is polar. It's a polar molecule. Okay, so here's some diagrams of molecules, and the colors emphasize which side is positive, which side is negative. So red indicates the most electron-rich area. That would be the delta minus side. And blue indicates the least electron-rich area. That would be the delta plus side. So if we were to look at such a picture of HF, we know that the F is more electronegative, partial negative side. The H is partially positive. So that's how that would look with this color visual. HF is polar. There's water. The hydrogen's partial positive, the oxygen partial negative. So it would be, the oxygen would be the red side, the hydrogen the blue side, water is polar. And we see that shown in that middle diagram where we have partial positive. It's not shown as the usual small case delta, it's shown as a large case delta. I don't know. Anyway, so we have partial plus on the H side, we have partial minus on the O side. If we were to put that in an electric field, then the H would be attracted to the minus side, the O would be attracted to the positive side. I did that using that burette, which had just water in it, and the charged rod that I brought up to it, and it showed that water was attracted to the charged rod. Okay, ammonia. There we see a structure of it. Ammonia has the trigonal pyramidal shape. It has a lone pair of electrons on the end, and then the three H's kind of pointing downward. So trigonal pyramidal, it is polar. The ends have the negative, partial negative charge, the H the partial positive charges. So in our electric field, the N would line up toward the plus side, forcing the O to line up toward the negative side. And the arrow that is shown on the NH3 diagram, as well as shown on the H2O diagram, it is drawn to point toward the negative side of the molecule. Okay, so N would have the red end, H would have the blue end. Ammonia, NH3 is polar. CO2, so that's the last one here. So indeed, O is partially negative and C is partially positive, but notice, given the shape of the molecule, though the O on the left pulls electrons just as much as the O on the right, and drawing our arrows, they're opposite each other. That is to say, it's like an even tug of war. There's no winner. So if we were to draw the picture with the red and the blue, what we would see is, yes, the red is by the O and the blue is by the C, but it's balanced. And what that means is carbon dioxide is not polar. It is a non-polar molecule. If we put it into that electric field, there would be no organization. The CO2 would be all random in there. Okay, here is another example for you to work on. We have you to draw the shape. Go ahead and give the name of the shape, bond angles, go ahead and do all that stuff for practice. I guess why not? And then polarity, predict whether each one of those, based on the shape of it and what we talked about above, is polar or nonpolar. Does it have balance in it or not? Okay, our next topic is bond energies. So those are the energy in a bond. And we will see that we will use bond energies to calculate delta H's for reactions. Okay, so once again, it takes energy to break bonds, or energy is given off when bonds are made. If we look at CH4 forming C plus 4H, what we're doing is we're breaking each one of those CH bonds, and that takes energy. Dissociation of CH4, one carbon at a time, we have all gases here. So if we pull away one hydrogen, we have CH4 forming CH3 plus H. That takes 435 kilojoules of energy. If we take that CH3 and pull off another hydrogen, we have CH2 plus H. That takes 453 kilojoules per mole. of energy. We then take the CH2, we pull off one more hydrogen, getting CH plus H. That takes 425 kilojoules per mole. If we take off that last hydrogen, so we have CH forming C plus H, that takes 339 kilojoules, giving us that 1652 kilojoules per mole to totally break CH4 into its atoms. If we take that 1652 and we divide it by 4, we get 413 kilojoules per mole as an average CH bond energy abbreviated often BE. So the energy per bond. This is done for many molecules, and average bond energies are tabulated and used to estimate delta H of a reaction involving those kind of bonds. So keep in mind, it takes energy to break a bond, and energy is given off when a bond is formed. So break a bond, endothermic, takes energy. Form a bond, exothermic, gives off energy. Delta H for a reaction using these bond energy values is the sum over N, the moles, times the bond energy of each broken bond minus the sum over N times the bond energy of each formed bond. So broken bonds, positive, that's why we do it with no negative sign in front. And then we have formed bonds, exothermic, that's why we have the minus sign there. Okay, so remember that sigma, that Greek symbol sigma is the symbol that in this case means to sum, to add together all of those. N is the number of bonds of that type, moles, I guess we could say. Be is the bond energy for that type of bond. Okay, so here are average bond energies in kilojoules per mole. So we have that 432 for C8, for that HH. Here we have CH, the one we calculated above, 413. Notice that when we have multiple bonds, that would be in the last column, a double bond, CC double bond is 614 kilojoules per mole. A CC triple bond is 839. So triple bonds greater than double bonds if we're comparing the same atoms. For C double bond O, unless it's C double bond O part of CO2, the value is 745 kilojoules per mole. Look down to the asterisk at the bottom of the table, and we see that C double bond O in the molecule CO2, that's 799 kilojoules per mole. So we're going to be using these values to do a calculation. And it is calculate delta H for the reaction H2 plus Cl2 forming 2 HCl. So we're after delta H of that reaction. So what we have to do is write out the Lewis structure of each of those reactants and products. So we have H, Cl, Cl forming HCl and then plus HCl because there's two of them. So delta H is the number of moles of the HH molecule. So there's 1 mole times its value. We look back at the table, so we're looking at HH. Here is our table. There's HH, 432 kilojoules per mole, plus the energy to break one Cl-Cl bond. In our table, we see that value is 239 kilojoules per mole. And then we're subtracting the energy to break, or we're subtracting the energy that's given off when the HCl bond forms, and 2 of them. So we have 2 moles times the value for HCl, which according to our table is 427 kilojoules per mole. And we calculate delta H to be negative 183 kilojoules. Notice the mole cancels out. Okay, now I give you this last problem to do. Example, calculate delta H for this reaction. CH4 plus 2O2 yielding CO2 plus H2O. You will have to draw out the Lewis structures for each reactant and product and do like we did in that above example. All the answers are in, as usual, this answers area. So go over the problems, read through look at this video as many times as is helpful for you. Read over your handout, Chapter 8 handout notes at your own rate. Read the Chapter 8 book, Zoomdoll book. Do the assigned homework that is posted in the syllabus. And do all the problems within here. Go over the ones we went over together. Go over the ones we didn't go over together on your own. And you will have a lab exercise, or I'm sorry, you will have a lab activity on this called, I believe, Lewis structures. And yeah, so any questions, you can always email me about stuff. Alrighty, so that's all.